1 over x. So what we want to do is just extend that a little bit. Basically, as long as x is positive, the natural log of the absolute value of x is exactly the same as the absolute value, as the natural log of just plain old x, as x is positive. Could be different if x is negative. So I want to take the natural log of the absolute value of x and write it as a piecewise defined function. Basically, there's a case when x is greater than 0, there's a case when x is less than 0, and what happens when x is equal to 0? What would be the value of this function?
It's undefined.
It's undefined, that's right. Absolute value of 0 is 0, natural log of 0 is undefined. So there's a case when x is greater than 0, there's a case when x is less than 0. So this would be just the natural log of x. If x is positive, absolute value of x is equal to x, and so this is just the natural log of x. If x is negative, when we take the absolute value, of x, we get negative x. The negative sign is to make it positive, right? X itself is negative, so put a negative sign there and make it positive. So that represents a positive quantity, and then we can take the natural log of that positive quantity that's inside the parentheses. So what we want to do is differentiate this on each of these open intervals. The open interval from 0 to positive infinity, and from negative infinity to 0, and come up with an expression for each one. Well, we've got an expression for the first one based on what we did last time. So this is going to be 1 over x if x is greater than 0. That's the natural log function, and it's a normal domain. X is greater than 0. And if x is less than 0, we can use the chain rule to differentiate that expression. So let's find, kind of off in the margin somewhere, d dx of the natural log of negative x. Let's see what we would do here, and I guess I should scoot it over just a little bit, give myself enough room here to apply the chain rule. This is going to be derivative of the natural log of the expression is 1 over that expression times the derivative of that expression. Chain rule says multiply by the derivative of what's inside the parentheses. So we multiply by the derivative of negative x. So this is going to be 1 over negative x times, what's the derivative of negative x? Negative 1, which simplifies to equal what? 1 over x. So here's the thing. If x is positive, the natural log of the absolute value of x is 1 over x. And if x is negative, the natural log of the absolute value of x is 1 over x. So as long as x is not 0, in which case it's undefined, the derivative of the natural log of the absolute value of x is 1 over x. So we could simply say this equals 1 over x. And we don't have to say provided x is not 0, because this expression is undefined if x is 0. So this is what we get. So it's nice that that adding the absolute value bars doesn't give us a new expression that we have to memorize. That would be a real pain. Okay, so see, how much can I shrink that down? Put that over there for reference. d dx then of the natural log of the absolute value of cosine x, we could do using the chain rule. Since now we know the derivative of the natural log of the absolute value of x, this is going to equal 1 over cosine x times the derivative of cosine x. So this equals 1 over cosine x times negative sine x.
What equals negative tangent x?
Equals negative tangent x, like that. some point we'll run across tangent x, and we'll wonder one way you can take the derivative of to get tangent x as the answer. It's going to be -1 times this expression, negative natural log of absolute value of cosine x. Perhaps that will occur to us, perhaps it will not, but there'll be an integration technique that we can use to find it in case it doesn't. So negative tangent x there. All right. Implicit differentiation. A lot of words on the first page here. Basically, I want to point to a couple of expressions. And then the first example is where I want to spend a good bit of time introducing the idea of implicit differentiation. Given an equation with x's and y's in it, then we just write it down. Left-hand side, 2xy minus x. Right-hand side, 3y plus 2. Put an equal sign in between them. There's a graph associated with that. It's a set of all ordered pairs in the plane that make that equation a true statement, the graph. Sometimes when we do that, we get something that defines a function of x. It'll pass the vertical line test. Sometimes, if we write down an equation with x's and y's in it, it won't pass the vertical line test. But in most cases, when we write it down using the expressions that we're comfortable dealing with, x is raised to whole number powers, sometimes x is raised to fractional powers, sometimes put x's and y's in the denominator. Most of the time we get the graph, if there are already points that satisfy the equation, will be, at least in pieces, nice smooth curves, where it would make sense to ask, well, if we draw the tangent line to that nice smooth curve, what would be the slope of the tangent line? Now, it might be difficult to express that in terms of a single variable. If it's not a function of x, it might not be possible to express the slope of the tangent line as a function of the x coordinate. But what we might be able to do is write the slope of the tangent line as a function of both of the coordinates. That is, tell me the x and the y coordinate. I can have an expression with x's and y's in it that I can substitute the x coordinate for x, the y coordinate for y, and simplify or evaluate, and that'll tell me the slope of the tangent line. So when an equation is defined implicitly like this, we don't have y all by itself on the left and nothing but x's on the right, but we got a mixture of x's and y's here and there on both sides of the equation. We'd like to be able to come up with an expression that will tell us the slope of the tangent line to occur. Now, in this particular case, you can solve it for y, and it turns out that it is a function of x. Y equals x plus 2 over 2x minus 3. Won't take the time to do that. We do that in college algebra. But this one is a function of x, and when that happens, we can compare. We can find the derivative explicitly using the quotient rule is what it would be to differentiate that expression right there. Find the derivative explicitly in terms of x, and then find a point on the graph and kind of compare what's the value of the slope of the tangent line if we use the expression just in terms of x, or if we go up here and differentiate implicitly. Haven't done it yet, but we will soon. What would the slope of the tangent line be if we know the x and the y coordinate of that point? This particular one, because it involves the product rule to differentiate the expression 2 times x times y, I'm going to save that until after example 1. But it's not going to be too tough to differentiate that implicitly. As far as the process, what I want to do with example 1 is a little bit more familiar. The picture is a little bit more familiar. I think this will be a nicer introductory example for this. We've got a circle centered at the origin with a radius length of 5. And we know this is not a function of x because it fails the vertical line test pretty badly. But we can write it if we look at the top half of the graph and solve this equation for y. We can write it as y equals the square root of 25 minus x squared. That'll give the equation of the semicircle that is the top of the graph. And then y equals the negative of that, negative square root of 25 minus x squared. That's the semicircle that's the bottom of the graph. First, we want to find the derivatives using the chain rule and the power rule that we've been using. Find them explicitly in terms of x, and then we'll go back to this original equation and differentiate implicitly and compare. See if we get the same answer. So first, the explicit derivatives. So nothing new just yet. Let's consider y equals 25 minus x squared raised to the 1/2. Let's see if we can find the derivative of this. dy dx. dy dx equals, now we're thinking chain rule. We know how to take the derivative of something raised to the 1/2 power. To take the derivative of something, some expression raised to the 1/2 power, we would bring the 1/2 out in front, and then we would reduce the exponent by 1. Now, according to the chain rule, the function u, or the expression u, could be substituted. We could let u equal 25 minus x squared. That's what would go inside the parentheses, 25 minus x squared. But then we have to multiply by the derivative of that expression. So then we multiply by negative 2x. Derivative of 25 minus x squared is negative 2x. Chain rule says multiply by the derivative of what's inside the parentheses. So we multiply by that. And then we simplify. dy dx equals, let's see how to do this. 1/2 times must be a neat, clean way to do this. But I don't think writing the 1/2 there really helps. I want to write a fraction, and I want to write 25 minus x squared to the 1/2 power in the denominator. I suppose I could put a 2 down there in the denominator and a negative 2x there in the numerator. That might be easy to see. The 1/2 gives us the 2 in the denominator. And then we can divide this 2 by 2 and get 1. Divide this negative 2 by 2 and get negative 1. So what we'll get is dy dx equals negative x over the square root of 25 minus x squared. So at that point, if we want to find the slope of the tangent line anywhere on the top semicircle, we can do it. So if we want to find the slope of the tangent line at the point 3, 4, that's on the top semicircle, all we need is the 3, because this is given explicitly in terms of x. So all we have to do is substitute 3. So we'd say dy, and actually I'm short of space. Let's shrink it. There we go. We'd say dy dx, x equals 3. It's kind of awkward notation. It'd be nice if we could just maybe put the 3 in parentheses, but sometimes we need to specify just the x, sometimes we need to specify both the variables. So we usually do it like this. This will be negative 3 over the square root of 25 minus 3 squared. So that's negative 3 over the square root of 16? Yes. And that's negative 3/4. So would this line, this tangent line, pass for one that has a slope of negative 3/4, you think maybe? Certainly negative. 3 down, 4 to the right, 3 down, 4 to the right. Slope of negative 3/4. Let's try it with the bottom half. If we want the bottom half, there we go. we would need to use y equals negative 25 minus x squared to the 1/2, bottom semicircle. So dy dx equals negative 1/2 times 25 minus x squared to the negative 1/2 times the derivative of what's inside the parentheses. And incidentally, here's where you want to use the constant multiple rule, right? We know the derivative of the square root of 25 minus x squared. The derivative of negative 1 times that, shouldn't that be negative 1 times the derivative we just got through finding? Yeah, we'll double check at the end and make sure that it is. But this will be dy dx equals negative 2x up there, 25 minus x squared to the positive 1/2 down there. And let me just call it positive 2x because it's a negative times a negative. I don't think I want to put a negative 2 down in the denominator. That would just feel weird. So let me just make that plus 2 there. So dy dx equals 2x over the square root of 25 minus x squared. Yeah, the 2 goes away. So what should I have done? Put a positive 2 down there?
Yeah.
Yes. That would have worked out better. Okay. So yes, x. This is negative 1 times the derivative we just found. X over the square root of 25 minus x squared. So if I wanted to find the slope of the tangent line at the point 4, negative 3, that's on the bottom semicircle. 4, negative 3 right there. So what I would need to do is use this other expression. I would have to say dy dx, where x equals 4 is equal to 4 over the square root of 25 minus 4 squared. That's 4 over the square root of 9. 25 minus 16 equals 9. So that's 4/3. So the slope of the blue line, m sub tan there, was negative 3/4. M sub tan for the red line, 4/3. What we would like is a single expression, possibly with both x's and y's in it, where if we pick any point on this circle, except maybe 5, 0 and negative 5, 0. Because I'm thinking the tangent lines there are going to be vertical, and the slope of those will be undefined. Any point on the circle except those two, we'd like to be able to substitute the x-coordinate for x, the y-coordinate for y, and it tell us the slope of the tangent line, and in such a way that we don't have to know whether we're on the top semicircle or the bottom semicircle. It ought to work either way. So, I've done everything except this part. We differentiated explicitly, now we want to differentiate implicitly, and in the process I got to explain how to do this. So here goes. Well, we start with x squared plus y squared equals 25. Okay, we don't, that's, I guess, the beauty of the implicit differentiation. Number one, you don't have to solve for y in terms of x. And maybe number one is really the only point that I need to make there, because sometimes it's not possible to solve for y in terms of x. It was kind of in this case, if we allow the plus or minus. But in general, it might not be possible. You could write a hideous expression with x's and y's in it that you just can't solve for y in terms of x, but you can still find an expression for dy dx. Here goes. Want to differentiate both sides with respect to x. d dx of x squared plus y squared equals d dx of 25. The ddx of 25 is no trouble. That's a constant. Derivative of a constant is 0. And on the left, really have to think about the sum and difference rules. They seem pretty straightforward when we used them to differentiate polynomials, but here it's the derivative of x squared plus y squared. We really need to think the sum rule says this is the derivative of x squared plus the derivative of y squared. I think it's good to separate those because one is an explicit expression in terms of x and the other has a y in it. We have to think, well, what's going on with that y? ddx of x squared is exactly what we would think it is. It's 2x. ddx of y squared, well, it starts with a 2y, but what happens here, because the variable in the expression and the variable with respect to which we're differentiating are different, y is a function of x, we really have to think chain rule here. See, y could be written like this, or it could be written like this, and it's almost like it's one of those expressions squared. So we got to think in terms of the chain rule. So it's going to be, how do you take the derivative of something squared? We'll take the derivative of something squared. It's 2 times that something, but the chain rule says multiply by the derivative of what's inside the parentheses. Well, what's inside the parentheses is the expression that was being squared. So we have to multiply by the derivative of y. We might not know y in terms of x, but we know we got to multiply by the derivative of y. So it looks like that. Now, if it looks like I'm not treating x and y the same way, had I multiplied by the derivative of x with respect to x, that's just 1. So I didn't take the time to do it. But here it's absolutely necessary. Multiply by the derivative of y with respect to x. Well, we have notation for that. The derivative of y with respect to x is dy dx. So we start off with an expression that defined an implicit relationship between x and y. Now we have an implicit relationship among 3 quantities: x, y, and dy dx. Now the result of this will typically give us an expression that's linear in the expression dy dx. So we can solve this explicitly for dy dx in terms of the other variables. So I want to take this, isolate the term that has the dy dx in it. I want to say 2y dy dx equals negative 2x, and then do what? Divide both sides by 2y. That'll give us dy dx all by itself on the left. So dy dx equals, so the 2's divide out, and we have negative x over y. And except in cases where y equals 0, the point 5, 0 and negative 5, 0, where there's a vertical tangent line, this expression is going to work all the way around the circle. Negative x over y is going to give us the slope of the tangent line. So if we try that at the point 3, 4, negative x over y, that's negative 3/4. If we try it at the point 4, negative 3, negative x over y would be negative 4 over negative 3, and that's positive 4/3. So we don't need 2 separate expressions to come up with the slope of the tangent line. Negative x over y works for every point on that circle. All right, now I don't have a lot of extra time to burn, but at the risk of doing that, all right. So we've got the graph of x squared plus y squared equals 25. And the coordinates of this point are controlled by, or can be controlled by, the sliders A and B. I can move it to the right and to the left by moving A, and up and down by moving B, so we can adjust the coordinates there. A good question might be asked, we've got this expression, dy dx equals negative x over y. That's what it was, negative x over y. If it's a point on the graph, that gives the slope of the tangent line. But what if we don't have a point on the graph and just plug in an x and y that are not necessary, that do not necessarily represent the coordinates of a point on the graph? What's the significance there? Well, I'm just going to grab the point rather than move the sliders. As long as it's on the circle there, that represents the tangent line, basically the expression that I have, negative x over y, negative 4 over 3 in that case. And I can drag it around, find another point on the circle. Of course, it's undefined right there. Various other points on the circle. There's another point on the circle, and so on. But if it's a point right there, what's really the significance? It's just kind of out there. Well, if we had we did x squared plus y squared equals 25, and we found dy dx was equal to negative x over y. What would we have gotten if it had been x squared plus y squared equals 16? Same thing. What about x squared plus y squared equals 9? Same thing. X squared plus y squared equals any positive number, basically, to give a circle with any radius that you want. Negative x over y would give the slope of the tangent line. So if we take this and put in a few more circles, put in that circle and that circle, if we grab the point and put it on any of these circles, that circle or that circle or that circle, negative x over y is giving us the slope of the line. It's going to be the tangent line to that circle wherever we put it there, and it doesn't matter which circle that we put it on. So negative x over y, as long as the circle is centered at the origin, is going to give the slope of the tangent line. All right. So differentiating with respect to x is no trouble if the expression is given explicitly in terms of x. But if there's some other variables mixed in, we want to make it as clear as possible how to carry out this process. So let's see if we can make sense of this in example 2. And yes, I believe I have 9 distinct examples here. Hopefully I do. d dx of x cubed, exactly what we would think it would be, 3x squared. But d dx of y cubed, assuming that y may be a function of x, would be 3y squared, but the chain rule would have us multiply by the derivative of y with respect to x. So it's 3y squared. I can throw in an extra step if you like to, but at some point, you know, you don't want to have to watch me do that. So you just want to say 3y squared times dy dx. It's a rough looking x. There. 3y squared dy dx. In the section on related rates, there'll usually be 2 or more quantities that all depend on time. Time is passing, and each of those quantities is changing, and there's some relationship among those quantities, but as time changes, they each change. So what we're going to want to do is compare the rates at which they're changing with respect to time. As time passes, how are they changing? So we'll differentiate a lot of variables with respect to t. So that'll be common. d dt of x cubed is going to be 3x squared times, if x is a function of t, if x changes when time passes or when t changes, we have to multiply by the derivative of x with respect to t. So basically I'm multiplying by d dt of x. And that happens when the variable in the expression and the variable with respect to which we're differentiating do not match. When when one is a function of the other. d dx of sine x, well, that's easy. It may not be easy, but we've done it before. We've memorized it. d dx of sine x equals cosine x. How about d dx of sine y? Derivative of the sine of something is the cosine of that something times the derivative of that something. So we multiply by dy dx. And the t and the x do not match in d dt of sine x. So the derivative of the sine of something is the derivative of that something as well. It's, sorry, the cosine of that something, cosine of x, times the derivative of that something with respect to t. Does it look like I've treated B and E in a similar manner and C and F in a similar manner? G, H, and I. Almost think I should have saved those for a separate page and maybe stretched them out a little bit. So I'm going to move G to the next page. Maybe blow it up a little bit. I don't know if that helps. Not enough pixels there. d dx of x squared y squared. Are you thinking product rule?
Yeah.
We should think product rule. Because if it were just x squared, we could find the derivative of x squared. And even if we're differentiating with respect to x, if it's just y squared, we can find the derivative of y squared. So we have two expressions, each of whose derivatives we know how to find. It's the product of them. So it's the first times the derivative of the second plus the second times the derivative of the first. Product rule. And then the individual derivatives that we have to find, we find them just like we found them in the previous examples on that page. So this is x squared. All right, d dx of y squared. Derivative.
2y times 2y.
There we go. 2 times that something times the derivative of that something with respect to x. So 2y dy dx plus y squared times 2x. And maybe clean it up a little bit, but not too much simplifying to do. 2x squared y dy dx plus 2xy squared. Now the next example I think is h, d dx, sorry, I was trying to contrast that, but d dy, isn't it, of x squared y squared? d dy of x squared y squared. And basically we'll get the same thing except reversing the roles of x and y. Pick up all the x's and put y's, pick up all the y's and put x's. And it should look like this. Again, it's the product rule. The first times the derivative with respect to y of the second plus the second times the derivative with respect to y of the first. It won't be often that we try to find the derivative with respect to y in the section. Actually, probably today, when we look at derivatives of some inverse trig functions, we'll find the derivative with respect to y. We won't do all that much of it. d dy of y squared, the variables match. It's just 2y. You could say 2y dy dy. but dy dy is just 1. So just 2y. And here, d dy of x squared, the variables do not match. So it's going to be 2x times the derivative of y with respect to x. And we would write that dx dy. So 2x squared y plus 2xy squared dx dy. And the I part, let's see if there's enough room for this. ddt of x squared y squared. Here x and y, perhaps independently, perhaps mutually dependent on each other and also dependent on time, are variables of t, functions of t. So it's the product rule, but there's a little bit more going on. There'll be a dx dt and also a dy dt in our final answer. So it's the first times the derivative of the second plus the second times the derivative of the first. So x squared, derivative of y squared with respect to t, is going to be 2y dy dt. And then y squared times the derivative of x squared with respect to t. It'll be 2x times the derivative of x with respect to t. And we write that dx dt. The variables don't match, so we have to multiply by that factor of dx dt in this case, or dy dt in that case. So 2x squared y dy dt plus 2xy squared dx dt. That's kind of warm up, kind of the sorts of things we would need to do if we had an equation that defined an implicit relationship between x and y. Back to here. Oh, maybe there. Yes. So, a couple more to look at. Use implicit differentiation. I'll capture as much of this picture as I can. Define dy dx if y plus cosine y equals xy. We would be hard-pressed to solve this equation for y in terms of x, although because it's not difficult to solve for x in terms of y, we can actually define a parametric curve and sketch a graph for this, either using the graphic calculator or I've done one with GeoGebra. But in either case, we can come up with an expression for dy dx in terms of x and y. So here goes. ddx of y plus cosine y equals ddx of xy. Differentiate both sides with respect to x. That's how it starts. On the left-hand side, it's the derivative of a sum. So the derivative of the sum is equal to the sum of the derivatives. So ddx of y plus ddx of cosine y. On the right is the derivative of a product, and for the derivative of a product, we use the product rule. It's the first times the derivative of the second plus the second times the derivative of the first. So we take the derivatives. d dx of y is simply the notation dy dx, the derivative of y with respect to x. Or you might say it's 1 times dy dx, but either way, that's what you get. Derivative of cosine y, derivative of the cosine of something, is the negative sine of that something times the derivative of that something. So minus sine y dy dx. Variable in the expression, the variable with respect to which we're differentiating, do not match. Y is implicitly a function of x, not explicitly a function of x, because it fails the vertical line test, as we can see here. But when x changes, y changes, so I have to multiply by dy dx. Equals x times the derivative of y with respect to x plus y times 1. d dx of x is 1. We need dy dx. So although we cannot find y explicitly in terms of x, we can find dy dx explicitly in terms of, well, a mixture of both x and y. What we want to do is get all the terms, there are 3 of them, get all the terms that have dy dx's in them together on the left-hand side. So the dy dx I'll leave where it is. The minus sine y dy dx I'll leave where it is. And the x dy dx I will subtract from both sides to have minus x dy dx, and then nothing but y on the right-hand side. What next? Factor out the dy dx. So get them all together on one side and then factor out that common factor. We have dy dx times the quantity 1 minus sine y minus x equals y. Then divide both sides by 1 minus sine y minus x, and dy dx equals y over 1 minus sine y minus x. So if we happen to know a point, any point on this graph, might not be the easiest thing to find, a point on this graph, but if we could find the coordinates of a point on this graph, we could find the slope of the tangent line by substituting the x-coordinate for x right here and the y-coordinate for y right there. So I'm suggesting that this point right there is actually on the graph. I think we should confirm that. Let's see if it's really on there. So if I substitute pi for y and pi minus 1 quantity over pi for x, I just want to confirm that it's a true statement and not something I just made up. I did make it up, but I think it's also true. Pi plus cosine pi equals maybe pi minus 1 over pi times pi. True or false? I guess if I erase the question mark, I can say true or false, but I'm not going to erase the question mark because it's still an open question. What's cosine of pi? -1. So pi plus -1. I'm thinking so. This equals pi minus 1. So yes, all I'm doing is confirming that sure enough, the point pi minus 1 over pi comma pi is actually a point on the graph. And it is. So, when we substitute pi for y in this expression, and down here, pi minus 1 over pi for x, it will actually tell us the slope of this tangent line. So we do it. I'm going to write it like this. Dy dx, where x, y equals pi minus 1 over pi comma pi. I really would like to have room to say something. What can I say? Oh, I can scoot this over. Let's shrink it just a bit. And then this over there. So dy dx, where xy is that point, is equal to pi over 1 minus sine pi minus pi minus 1 over pi. Substituting pi for y, pi minus 1 quantity over pi for x. Let's see what we get. This equals pi over 1 minus, what's the sign of pi? 0. Yeah, so sine, what? Sine starts at 0, and then over at pi, it's equal to 0 again. So it's 0 minus, I'm going to take this and write it pi over pi minus 1 over pi. How much more room do I have? Pi over 1 minus 1 plus 1 over pi. If we cancel the 1 and the minus 1, it's pi over 1 over pi. It's pi times pi over 1, pi squared. Yeah, this is pi squared. So the slope of the tangent line, m sub tan, equals pi squared. All right. Can't say too much about how I put this together because I just learned today, first time I really needed to do a parametrically defined curve in GeoGebra. So I'll show you the finished product. Forgot to turn the recording back on.
On the right side of any text entry.
Yeah, I've got to scoot that. Ah. If I type in it right there, yep, it should let me enter pi. And it should know what that means. Yep, that works. So you just enter the pi character there. And that works. But the parametric equation worked nicely in this case. All right. This one is a little bit on the... Well, I don't know if this is going to add this much more to our discussion. In lieu of example 4, what I would like to do is go back to the very beginning and let this be my example 4. This one right here. And I want to see if I can find the derivative of this using implicit differentiation. How am I going to do this? Where's example 4? Yeah. There, so a little bit of editing. Let's do this. 2xy minus x equals 3y plus 2. This should be actually a little bit nicer example. But let's see what we get. d dx of 2xy minus x equals d dx of 3y plus 2 d dx of 2xy minus d dx of x equals d dx of 3y plus d dx of 2. What this has, that the cosine example did not have, is the product rule. So a little bit more going on with this. Not something we haven't done yet this hour, but a little bit something different. To find the derivative of 2xy, I could do a couple things. I could yank the 2 out in front. 2 is a constant, so you could pass it through the d dx notation, and we could say this is simply 2 times d dx of xy. But then we have to keep track of the parentheses around that expression and then eventually distribute the 2 across the parentheses, and I don't want to do that. So I'm going to treat the 2x as one expression and the y as another, and I was to think of it as the product of those 2 expressions. I mean, if you wanted to, you could dissociate the 2 with the y, but that's what I want to do. Got to do something with the 2, and that's what I'm choosing to do with it. So it's the first times the derivative of the second plus the second times the derivative of the first, product rule, minus the derivative of x, d dx of x, that's 1, equals d dx of 3y. Well, in that case, it'd probably be nice to take the 3 and drag it through the d dx notation, because it would be 3 times the derivative of y with respect to x, but that's 3 dy dx. d dx of 2? 0. So plus 0 or just ignore it. 2x dy dx plus y times 2 minus 1 equals 3 dy dx. Get the dy dx's together on the left-hand side, and it will look like this. 2x dy dx minus 3 dy dx. What's the other side of the equation going to look like? Either 1 minus 2y or negative 2y plus 1, whichever you prefer. I think I might prefer 1 minus 2y, but ask me again on another day and I might prefer negative 2y plus 1. So I'm going to go with that. Factor the dy dx out of each expression on the left, and it'll be 2x minus 3 times dy dx equals 1 minus 2y. And dy dx then equals 1 minus 2y over 2x minus 3. So if we could find a point on this graph, we could substitute the coordinates into 1 minus 2y over 2x minus 3, and it would give us the slope of the tangent line. All right. So this is the graph. It actually did define a function. We didn't go to the trouble of finding it, but it turns out that if you take this equation and solve it for y in terms of x, you get y equals x plus 2 over 2x minus 3. So it does define a function, and the graph looks like that. And what I've done is had a and b represent the x and y coordinates of this point, and then over here m is that expression 1 minus 2b over 2a minus 3. Is that what we got? 1 minus 2y over 2x minus 3. So m is going to be what you get when you take the x and y coordinates of this point and you substitute them into that expression. Well, if it's just off here somewhere, who knows what could be meant by the slope of that tangent line, but if it's a point on the curve, it's the slope of the tangent line. Slope of the tangent line. So right there, or over there, anywhere on the curve, down here, it's going to be the slope of the tangent line. What's the significance if it's out here somewhere? Well, there might be various different ways to interpret that. Really not much as far as this function is concerned, but consider this. Remember we did the circle and said suppose it had been not a radius of 5, but a radius of 4 or 3 or 2. Basically, we had a family of circles, all centered at the origin. Well, there's a constant that we ran into when we were taking this derivative, and the constant was right there, d dx of 2. What if I change that 2 to something else? Not going to have any impact on the derivative, but it's going to change the original function. Basically here, we could change this number. Where it showed up in the original was right. Let's see, if we take this and solve it for y, there are a couple of 2's. I want to make sure I get the right one. I believe it ends up right there. I believe that's where that 2 ends up. Yes, it does. If we change that 2 to something, we get a different graph, but somehow our expression should still work as the slope of the tangent line. So consider this. What we have here is the graph of f of x equals x plus 2 over 2x minus 3. If we say, what if we say g of x equals x plus 5 over 2x minus 3? Well, that tweaks it a little bit, but if we move this point onto the green graph, if it's on that graph, it's the slope of the tangent line. We could do another one, change the 2 to an 8, and that gives us that curve. If we take that point, out here it doesn't mean much, but if it's on that curve, it's the slope of the tangent line. If it's on the curve over here, it's the slope of the tangent line. Or we could do, I had one more, but then there's a nice way where, try it sometime, you can define a sequence of whatever you want, sequence of points, sequence of curves. And so I just did a bunch of them, whole family of curves, and all I'm doing each time is changing that number. This expression we have for the derivative, if it's on any one of these curves, where it is, it's the slope of the tangent line for this entire family of curves. Now when you study differential equations, you get a little bit more out of that, and you can take it a little bit further. But I think as far as the expression having meaning, when we move the point off the curve, well, maybe we're moving it onto another curve where it's also the derivative of that expression, or at least give you the slope of the tangent line. All right, let's take a short break. One more technique from this section. I'm not going to do example 5. Example 5 is worked out, so I'm not going to do the details of that unless you run across a situation where you need to find the second derivative using implicit differentiation. If you run across one of those in the homework, then perhaps when we stop to review for the test, I can give that a little bit of attention. But I want to make sure that we have kind of a appreciation for the technique of logarithmic differentiation. It actually works in situations where we'd probably not go to it naturally. I've seen students, I give a problem on a test, say find the derivative, and I won't expect them to use logarithmic differentiation, and they will, and it turns out to be easier. It's the idea to exploit the properties of logarithms to make differentiation easier. That's the idea, although it sounds horrible. We want to find the derivative of y with respect to x really explicitly for this expression, and this would be awful. This is kind of one of the ones where we use the quotient rule, and inside the quotient rule we've got the product rule, the numerator, and the chain rule in the denominator, and inside the product rule, the numerator, we've got the chain rule going on some more. We don't want to do all that. So what we do is we begin by taking the natural log of both sides. Of course, we hope y is positive now in order to do this, but it's going to work out. Natural log of y equals the natural log of x squared. I'm going to write it sine x to the fourth over 4x minus 9 to the 1/3. Take the natural log of both sides. Before we take any derivatives, simplify the right-hand side as much as possible. Expand that logarithm just as much as the properties of logarithms will allow you to expand it. So on the left, we just copy and paste. On the right, the log of a quotient equals the difference of the logs. So log of the numerator minus the log of the denominator. And then the log of this product, x squared times sine of x to the fourth, is equal to the sum of the logs. So natural log of y equals natural log of x squared plus natural log of sine of x to the fourth minus, and this logarithm really is not too much more we can do except take that 1/3 out in front. So 1/3 times the natural log of the quantity 4x minus 9. And then as we did that, the 2 can come out in front, the 4 can come out in front. So natural log of y equals 2 natural log of x plus 4 natural log of sine x minus 1/3 natural log of 4x minus 9. Careful, don't want to go too far. We don't have a nice property for the log of the difference, the log of 4x minus 9. I'll sometimes see that done, but we just have to leave that log of 4x minus 9. We can't push that any farther. Now, we're in a position to take derivatives. Because, yeah, we're composing the natural log with some expressions, but it's not nearly as awful as it would have been otherwise. Because I could shrink that down a little bit. I hadn't thought of that. Let's do this. Need space. All right. So differentiate both sides with respect to x. It's going to be d dx of the natural log of y equals, I'm going to go ahead and differentiate term by term on the right-hand side, or at least write it out that way. d dx of the entire right-hand side would be d dx of 2 natural log of x plus d dx of 4 natural log of sine x plus d dx, minus d dx of 1/3 natural log of 4x minus 9. On the left, d dx of the natural log of y is the only place we really need to use implicit differentiation. But it's for that reason that we did implicit differentiation first and then did the logarithmic differentiation. d dx of the natural log of an expression is 1 over that expression times the derivative of that expression with respect to the variable, with respect to x. So 1 over y dy dx. Over here, it's all explicit. d dx of 2 natural log of x is going to be 2 times 1 over x. A little bit of chain rule. d dx of 4 natural log of sine x is going to be 4 times 1 over sine x times the derivative of sine x cosine x minus 1/3 times 1 over 4x minus 9 times the derivative of 4x minus 9. 4. So, actually a couple more steps. 1 over y dy dx equals 2 over x plus, I'm going to call it 4 cotangent x. minus 4 over 3 times the quantity 4x minus 9. I want to do two things. I want to write this so that I have dy dx all by itself on the left. So I need to multiply both sides by y. So we can do that. Maybe up here. Dy dx equals y times everything we had on the right, 2 over x, plus 4 cotangent x minus 4 over 3 times 4x minus 9. And if we were differentiating implicitly, this would probably be a good way to leave the final answer. But the problem really is expecting an explicit expression for the derivative, basically nothing but x's on the right-hand side. Because that's the way it was given. It was solved for y in terms of x, so we should have dy explicitly in terms of x. So one more step. Pick up the y and replace it with x squared sine to the fourth x over the cube root of 4x minus 9. So dy dx equals x squared sine to the fourth x over the cube root of 4x minus 9 times 2 over x plus 4 cotangent x minus 4 over 3 times the quantity 4x minus 9. Looks like this. Oh, sorry. In the time that remains, I want to see what I can say about, and we'll use that picture in a moment, about derivatives of inverse functions. I haven't found this definition, or it's really not a definition, it's a theorem, to be terribly practical with what we need to do with derivatives of inverses. I just want to make some observations based on the graph. We know the relationship between the graph of a one-to-one function and the graph of its inverse. Make some observations there, and then what we'll do is we'll use this relationship. Dy dx can actually be written as 1 over dx dy. We're still not officially thinking of dy dx as a fraction or dx dy as a fraction, but if we write an expression for dy dx, possibly in terms of both x and y, and then maybe redo the problem and differentiate with respect to y, and write an expression for dx dy, possibly in terms of x and y, it turns out that one is in fact the reciprocal of the other. And let's see, I just want to look at a graph of a one-to-one function and its inverse and see if we can see why that ought to be the case. So this picture, in a moment, we will look at the function, I believe it's right here, f, let's go blue, f of x equals x cubed plus 3x plus 2. This can be shown to be a one-to-one function, and let's just indicate why. F prime of x equals 3x squared plus 3. Now, we don't officially show this until we talk about the mean value theorem a few sections down the way, but if a function has a derivative and that derivative is always positive, I think we can even relax that a little bit and say it's always, no, let's say it's always positive. I was going to allow it to be 0, but then I worried. Its derivative is always positive, then the function, the tangent line is always slanted upward, the function is always increasing. And a sufficient condition, not necessary, but a sufficient condition for a function to be one-to-one is that it be increasing on its entire domain or decreasing on its entire domain. If either one of those happens, it's guaranteed to be a one-to-one function and thus would have an inverse. This one, 3x squared plus 3, is always positive. Right? So this one, it looks pretty steep, but we've basically shown that this one right here is increasing on its entire domain. Now, if we find dy dx, dy dx is the slope of the tangent line to this graph. That one right there. dy dx, that's what that represents. It's the derivative, slope of the tangent line of that graph. Now, if we want to find the inverse of this function, we'd have a hard time doing it. Because remember the four-step process for finding inverses? You replace f of x with y, and then you interchange x and y, and then you try to solve for y in terms of x. If we were to do that, I mean, this is the graph of the inverse. This is y equals f inverse of x. But if we try to find an expression for that in terms of x explicitly, that's going to be hard, because what we would do is we would say, well, y equals x cubed plus 3x plus 2. X equals y cubed plus 3y plus 2. There exist formulas for solving cubics. We don't study them in college algebra because we just don't have that much of a use for them. So that's the equation. X equals y cubed plus 3y plus 2. That's the equation that's the graph of, but we just don't have an explicit expression for dy dx, well, for y in terms of x, but we can come up with an expression for dy dx in terms of at least x and y. Here's what we do. We find dx dy. Dx dy equals 3y squared plus 3. Okay, maybe a little bit unsatisfying. If we want to find the slope of the tangent line of that graph, we need the y-coordinate of the point on that graph. So here's how it goes. I believe the point 1, 6 is on the graph of this original function. Is it? Let's see. 1 cubed is 1. 3 times 1 is 3. 1 plus 3 is 4. Plus 2 is 6. So the point 1, 6 is on that graph. If I want the slope of that tangent line, rough looking tangent line. The slope of that tangent line, it's going to be, well, 3 times 1. Oh, this is unfortunate. It's also 6, isn't it? 3 times 1 is 3, and 3 plus 3 is 6. So m sub tan equals 6. That's the slope of the tangent line. Because we take the x-coordinate, we plug it in. Well, if the point 1, 6 is on the graph of a function, what corresponding point would be on the graph of its inverse? 6, 1. So the point 6, 1 would be on the graph of its inverse. And what would be the slope of this tangent line? Basically, the derivative of the inverse is what we're looking for. The derivative of the inverse, which tells the slope of the tangent line to the graph of the inverse. Well, we take dx dy is 3y squared plus 3, but dy dx is going to be the reciprocal of that. Dy dx, according to, well, I'm not doing anything or I'll lose everything I've written on this. Dy dx equals 1 over 3y squared plus 3. So if I take the y-coordinate is 1, and plug it in for y, I get 1/6. 3 times 1 squared plus 3, that's 1/6. 1/6. And these are reciprocals of each other. You can get that from the symmetry. You reflect about the line y equals x, so I hope it would make sense that the tangent line here and the tangent line here would have slopes that are reciprocals of each other. So we have the relationship dy dx equals 1 over dx dy. So it's kind of a little different approach than maybe what the calculus approach would have been, but that's, I think, the most useful take I have on that particular topic. So I want to take that and the fact that dy dx equals 1 over dx dy and go from there and see if I can find a derivative of an inverse trig function. Now, if you look through, I will, basically we did example 2 there. I go through and I just review some trigonometry. If we've got the sine function, there's a sine function, there's a graph, it's not one-to-one. So if you want to define an inverse function, we have to chop off most of the domain so that we're left with something where it is one-to-one on the domain. Basically, we want to be left with just this much. So it's called the restricted sine function, but it takes on the entire range. It includes the first quadrant, and it's as continuous as it needs to be. In fact, it is continuous. The domain is from negative pi over 2 to pi over 2, and the range is the same as the range of the regular sine function. So if we evaluate the inverse sine function at a particular number, say 1/2, well, this is the sine function, but the 1/2, what it would, inverse sine function would tell us the particular value that you can take the sine of to get 1/2 is the answer. So there would be a unique answer in that case. Well, I don't want to rehash all that for the sine, the cosine, the tangent, and how you define their inverses. But let's see, once we define their inverses in a good, healthy trigonometry class, let's see if we can find the derivative of one of the inverses. Trigonometry, 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 more trigonometry. d dx of arc sine of x, also known as sine to the -1 of x. How did your trig book define these? Arc sine or sine to the -1 of x? Sine -1 of x. Would it be more comfortable if I did that? I'm reasonably flexible when it comes to such things. Let's see. d dx of sine to the -1 x. Well, let's call this y. Let's say y equals the inverse sine of x. I want to find dy dx. Let's see what this is equivalent to. I believe this is equivalent to saying x equals the sine of y. Yep. X equals the sine of y. So what I want to do is find dx dy, take the reciprocal of that, and then try, if I can, to write it explicitly in terms of x. Finding dx dy is no problem. Taking the reciprocal of that is no problem. The challenge is to write it explicitly in terms of x. What is dx dy? Maybe even simpler than it seems, or as simple as it seems. It's cosine y, just like that. And because we're differentiating with respect to y, that variable matches the variable in the argument. We don't have to multiply by d anything. It's just cosine y. But if I want dy dx, dy dx is the reciprocal of this. Dy dx is 1 over cosine y. But what's y? Y is the inverse sine of x. And this is the challenging part. this is 1 over the cosine of the inverse sine of x. So we need an expression for that in terms of x. So it's right triangle time. It's right triangle time. Off to the side, off in the margin somewhere, we let theta. We can actually do this with y, but sometimes we don't think of y as an angle. So I'm going to go with theta. Theta equal inverse sine of x, so the sine of theta equals x. So here's theta. And if the sine of x, sine of theta equals, let's say, x over 1, let's write x as the side opposite and 1 as the hypotenuse. What would be the length of the other leg? The square root of 1 minus x squared, 1 squared minus x squared. The square root of 1 minus x squared. And if that's the case, what is the cosine of theta? The square root of 1 minus x squared. So here we go. 1 over cosine of inverse sine of x is going to be 1 over the cosine of theta. So that's 1 over theta as we've defined it up there, 1 over the square root of 1 minus x squared. So this is an expression for the derivative of the inverse sine function, 1 over the square root of 1 minus x squared. And let's see, derivative of the inverse cosine is similar. Let me see, does example 6 ask for the derivative of the inverse tangent? Let's try this one. Derivative of inverse tangent. I'm going to say y equals the inverse tangent of x, so that x equals the tangent of y. What's the derivative of the tangent of y with respect to y? Maybe I should say this, ddy of x equals ddy of tangent of y. Dx dy equals, it's as simple as it seems, if we remember the derivative of tangent, secant squared of y. All right, that's dx dy. What we need is dy dx. It would seem to make sense just to call that cosine squared y since I'm taking the reciprocal, but I'm going to call it 1 over secant squared y. No, I'm going to call it cosine squared y and see what terrible thing happens, because it just seems like the natural thing to do. Here's our triangle. So this equals cosine squared of what's y? Inverse tangent of x. So cosine squared of inverse tangent of x. Let theta equal inverse tangent of x, so that the tangent of theta equals x. Tangent is side opposite divided by side adjacent, so that's x over 1. And the hypotenuse then would be what? The square root of 1 plus x squared. So what is the cosine of theta?
Yes. 1 over.
One over the square root of 1 plus x squared. So 1 over the square root of 1 plus x squared. So it's 1 over 1 plus x squared. There we go.